Hi everyone, this is Kumar and welcome to Chemistry Tutorials. I'm doing a series of videos on general organic chemistry and we already did part 1 of this lesson, which was titled Introduction and Inductive Effect. And if you're a beginner and if you haven't looked into this video, I suggest that you go and have a look at that video first and then come back to this video. And I am putting the link of that video in the description below. Now, today's lesson is titled, this is the part 2 of 13, and this is titled Resonance Effect. Now, inductive effect was looking at an electron like a particle. If you have seen that video, we looked into the electron and we said it's here in the case of hydrogen, and when we change hydrogen with another group, it is pushed away from that group or pulled towards that group. So we were looking at the placement of the electron, the position of the electron. It was here, it moved here. We even looked at the various distances by which it is moved by different groups. So that is treating an electron like a particle. But as we know, electron has a dual nature. It also has a wave nature. So we wanted to understand how we can incorporate wave nature into the molecules and compounds that we study in the case of organic chemistry. Now, when you did bonding, and if you haven't and you're a beginner, I suggest you go and do bonding first before you even jump into organic chemistry. And in bonding, you must have done valence bond theory, which again treats an electron like a particle. We do the Lewis dot structure. The very act of drawing a dot for an electron implies we are treating it like a particle. But then we realize as we go on during the valence bond theory, there are a lot of properties of a molecule which cannot be explained by this simple valence bond theory, and that we need something more concrete and more encompassing the basic nature of the electron. And then we invented what is known as the molecular orbital theory, which then treats an electron like a dual behaving entity, both a particle and a wave. And its wave nature, we use the wave functions, and we take atoms and electrons which are forming the bond, we combine their wave functions, we superimpose those wave functions, and we say, okay, you have a constructive interference called bonding molecular orbital, you have the destructive interference called the anti-bonding molecular orbital, and so on. But this theory is so complex that we end up dealing only this theory for diatomic molecules, and that too preferably homonuclear diatomic. For heteronuclear diatomic, we literally have to learn the way the molecular orbitals are arranged in increasing order of energy. Basically, what molecular orbital theory does is that it assumes a molecule to be one entity. Rather than taking it as piece by piece, that it is bonded to this atom or bonded to that atom, it combines all those atoms, the wave functions of all the electrons, combines them with the other electrons of the other atom, and assumes then that now we have created a molecule which is one single entity, and it is described by its molecular orbitals, just like atoms are described by their atomic orbitals. Now, how do we understand the property of an element? An element's property is understood by, first of all, writing the electronic configuration, and then we look at how many unpaired electrons it has and blah 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 and various other things. Same thing is done for molecules using the molecular orbital theory. Once we have the molecular orbitals, we just have to fill those molecular orbitals just as we did in the case of atoms with atomic orbitals. But the problem with molecular orbital theory compared to the atomic orbitals is the fact that these molecular orbitals are not arranged in any particular order or any order which we can learn and reproduce for a majority of molecules. For example, in the case of atomic orbital, we follow the F-bow principle for filling the electrons, and which we used as an n plus L rule. The one with the lowest n plus L will get filled first. Of course, there are a lot of elements, especially in the case of F block, which violate this from time to time, but there are many of them which actually follow it. The majority follow it. But in the case of molecular orbital, there is no rule of that kind that we can use to write the molecular orbitals. So what we do, and that too, for diatomic molecule itself, it's a big pain. On top of that, when you go for polyatomic, it's even more painful, it's even more complex. Therefore, the right way would have been to use the molecular orbital theory for all the organic compounds also. But imagine, for a diatomic molecule itself, it is so complex, what will happen to a polyatomic molecule? It is going to be very, very cumbersome to do it. And it is quantitative. Molecular orbital theory is quantitative, it's not qualitative. What it does is that you have to mix all the wave functions and then get the value of the effective molecular orbitals, then place them, then put the electrons. It is very, very difficult to use molecular orbital theory, at least for the kind of approach that we are looking for. So, scientists decided that rather than trying to figure out how to use the molecular orbital theory in the case of complicated molecules, they said, why not invent something and use that and get the results from that such that it matches the results that we would have got had we used molecular orbital theory. And that effect is called the resonance effect. This effect primarily takes the wave nature of an electron, and we pretend to use resonance effect as if it's a real effect. But what it basically does is that it's an alternate route to reach the same conclusions of molecular orbital theory, which is the right one to use. But it is very complex. It's a sort of a bridge that takes you from the result of the valence bond theory to the result of molecular orbital theory. It's a bypass. It bypasses the molecular orbital theory approach and leads you to the same conclusion, which works for us. Anything that gets us the right result works. The theory may be hypothetical, may be real, as long as it gives us the right answers, it works. End justifies the means. So that is resonance effect. So let's begin this lesson with resonance effect. Okay, so the first thing that we need to understand, the effect by which the properties of a compound are explained, which otherwise cannot be explained by a single structure, by considering the actual structure to be a hybrid of several hypothetical structures, is called resonance effect. So basically, in the case of resonance effect, what we are assuming is that there is not just one structure, valence bond structure, which can explain the property of a molecule. If it can, great, then we don't have to bother about resonance effect. But if it cannot, then what we do is we write several structures, depending on the nature of the molecule or the ion, and then we say that the property of the molecule is a mixture of the property of each of these structures. But the molecule has to exist only in one particular structure. So what we say is that the actual molecule is a hybrid of these structures. These are parent structures. We call them as canonical forms. And we consider these things as real, but then later on, once we draw them, we say, okay, fine, they are not the actual structure of a molecule. The actual structure is a hybrid of this, combination of this, cross of these molecules, these structures. And resonance effect is due to the delocalization of pi electrons. So pi electrons are getting delocalized. The localized behavior is the inductive effect. The delocalized behavior is the resonance effect. It arises out of the wave nature of electrons. We already seen that. Now, since wave nature of an electron in a structure cannot be drawn, we represent hypothetical canonical forms which exhibit particle nature and whose hybrid the actual structure can be assumed to be. Now, in this regard, what I would like to say is that the very act of drawing something, the very act of drawing an electron means it's a particle because you're drawing it. Wave is delocalized, whereas a particle is localized. So the very fact that you are able to draw something and say, okay, a dot, the moment you make a dot, it implies the electron is localized. So we can only draw particle structures. We can never draw the wave structure. So what we say is that, okay, let's draw the particle structure, the ones that we can, and then let's take the hybrid where the electron is not just in one place, it's in multiple places at the same time. That is important about the wave nature. It is in multiple places at the same time, which is very difficult to conceive for a particle, but for a wave, it's okay. For example, if you're listening to me using a speaker, and if I were to ask you, where is my sound? Then my sound is everywhere, wherever you can listen to me. So wave is delocalized. So electrons are delocalized. So we cannot draw the wave nature of an electron, though we try to draw the hybrid using dots and all of that, but that is only trying to please ourselves by drawing it. That is not the actual structure, because you don't know how much is the dot density in one place. So all of that is not the accurate way of drawing the structure. The best way is draw all the parent structures and then just try and imagine, if you can, the hybrid. The actual structure of the molecule or ion is the weighted mean of the canonical or parent structures, but the energy of the molecule is lower than all the canonical forms. This is again a very important point. Now remember, the hybrid is the weighted average of all the structures. Let's say there is one structure which contributes 50%. There's one structure which contributes 30%. The other structure which contributes 10%. There's another structure which contributes 7%. There's another structure which contributes 3%. So if we were to look at or understand how the molecule would be, physically speaking, then it would be 50% of that structure which contributes 50% and various percentages as they are contributing to the actual structure. So the one to which, with the structure which contributes only 3%, the molecule will appear only 3% like that. So the actual molecule is the weighted mean of all of them. It has the characteristic 50% of the characteristic of the structure which contributes 50%, 3% of that structure which contributes 3%, that way. But the energy is not the weighted average. The energy of the resonance hybrid is actually lower than the energy of all the parent structures. So remember, the physical appearance is a weighted mean. The energy is not a weighted mean, it is lower than all of them. And the very fact that the nature allows resonance to happen, allows the electron to be like a wave, is to reduce energy. Okay, so while drawing the structures of the hypothetical canonical forms, we have to make sure that the position of atoms are to remain fixed while that of electrons change. Molecules showing resonance have to have a particular condition, that is, conjugation and the orbitals should be appropriately oriented. Conjugation means alternate. So those situations where resonance happens, there is something which is alternate to each other. And we will look into each of those conditions where resonance happens, and you'll understand what conjugation actually means. But conjugation basically means that here something or the other is alternate to another one. And it is alternateness, if I can invent a word like that, which is called conjugation and which gives rise to resonance. And apart from this, the orbital should be properly oriented. That means if a pi bond has to form, then the two p orbitals must be parallel, or as much parallel as they can be. The only situation where pi bond cannot form is when they're 90 degrees or more than 90 degrees. So they have to be at an angle. Parallel would be the best. Slightly off parallel is okay. So what we're trying to do is there has to be an appropriate orientation of orbitals for resonance to take place. Resonance effect is often referred to as mesomeric effect, and later on we will see a slight difference between the two, but for all practical purposes we can assume that they mean the same thing. Now, resonance effect is a permanent effect. Just like inductive effect, it's a permanent effect. It resides in the molecule from the day the molecule is born and dies when the molecule dies. So resonance effect is a permanent feature of the molecule. It doesn't happen suddenly. Resonance effect is a strong effect, generally stronger than inductive effect. And resonance is a relative effect, a very, very important point here. What does this mean? It's a relative effect. Well, it's a relative effect in the sense that inductive effect was compared to hydrogen. Everything was compared to hydrogen. So the inductive effects of all the groups were fixed. So ones which pushed compared to H were plus I, the ones which pulled compared to H were minus I. So we have designated them, categorized them. Whereas in the case of resonance effect, we cannot categorize them always. Some groups or atoms would always show plus R or plus M. Plus R or plus M means releasing electrons by resonance or mesomeric effect. And others would always show minus R or minus M. But there would be some which could also show minus R and plus R at different times. Not the same time, but at different times. So it's a relative effect. And those which always show minus R is because they're incapable of showing the characteristic of the molecule says that it is incapable of showing plus R. But if something can show plus R and minus R, it will in different situations. And we'll see all those conditions here. First, we'll do what resonance basically is, how to draw the structures, all the conditions when resonance happens, and then we'll deal with it. So remember, it's a relative effect. It is not the absolute property. So if somebody were to ask you, what is the resonance effect of a phenyl group or a phenyl group? And is it plus R or minus R? Well, it all depends upon to what it is connected to. And it's a need-based effect. Now remember, when we were doing inductive, I clearly told you a methyl group, CH3 group, or methyl group, if you may, has a plus I effect. It doesn't really bother whether the atom to or the group to which it is attached wants the electrons or not. It will push. Whereas resonance is not like that. The resonance is a need-based effect. Do you want electron? I'll give you because I can. Or do you have a lot of electrons? I need it. I'll take it from you. But if you are electron rich and I also have electrons to give to you, then the extent to which I might give to you would actually be much less. Or perhaps in some situations I might not even give it to you. Imagine resonance like the flow of current from the high electron density region to low electron density region. So unless or until there is a potential difference, the current cannot flow. And if there are two groups attached and the potential difference is zero, then it's not going to show resonance. So resonance is actually a need based. Do you need it? And how much you need it will also tell you how strong the effect would be. Alright, now before we start dealing with the cases of resonance, we need to understand the certain basic movement of electrons. So imagine this situation. And you're going to see a lot of arrows. Remember, a full arrow while showing resonating structure implies movement of two electrons. The tail is the place from which the electron is moving. Head is the place to which the electron is moving. Half an arrow basically implies one electron movement. So what would happen if it is shown like this? As you can clearly notice that the head of the arrow is somewhere else, whereas the tail of the arrow lies on this bond. This means, and it's a full arrow, that means both electrons of this bond are moving away to some other place. I'm not right now showing you where they are moving to, but it will suffice to know that the electrons have moved from this spot. So what would be the fate of A now? The fate of A would be that no longer there will be a bond and A would have lost one of its electrons of the bond and therefore A would become positively charged. So this is the result. What if the arrow was like this? What does this mean? The tail is on A, which means it is talking about this lone pair. And the head is on this bond. So A is using its lone pair to form a bond. Now when an atom loses or uses is the right word, both electrons or its lone pair to form a covalent bond, it's called a coordinate covalent bond. Take the case of ammonia for example. Now in the case of ammonia, N has a lone pair. H plus comes. And we know that ammonia forms a coordinate bond with H plus to form ammonium ion. And this is how you can assume it to happen. First of all, N would transfer one electron to H plus. Because covalent bond theory says that covalent bonds can only be formed when both share one electron. So N gives one electron to H plus. H becomes 0 now in charge, whereas N becomes plus because it has lost one electron, and now it forms a normal covalent bond with H. So in ammonium ion, the plus resides on N. The same fate awaits A here. A is forming a coordinate covalent bond using its lone pair. So what would happen is the bond would become double because now there is a new bond formed using the lone pair of A, but A would have effectively lost one because of the formation of the coordinate bond, and therefore its formal charge becomes plus. What would happen if it is a situation like this? Now this is a situation where the electrons are coming from some source, I have not specified from where, but they are coming to this bond, and since it is two electrons coming to this bond, and none of those electrons are those which belong to A is the receiver of the coordinate bond. The receiver of a coordinate bond will always get a negative charge. Remember, the H plus took one electron, became H, so one minus increased in it. It was already plus, so it became neutral. But had it not been positively charged before, on getting the electron, it will become minus. So here, in the case of this movement of electron, when an atom receives the coordinate bond, it's going to get a formal charge of -1. So in this case, the bond becomes double and A becomes negative. What would happen if it were like this? Well, here the tail resides on the bond, the head resides on A, which means both the electrons of the bond have moved to A, so the bond vanishes and A becomes -1 because one electron already belonged to that of A in this bond. It gains effectively only one electron. So bond vanishes and A becomes minus. Now let's take situations where this happens. Let's take this situation and let me draw an arrow like this. Now I want you to draw the result of this. Pause the video now. So wherever I'm going to give a particular product, pause the video, make it on your own, then check. That is the only way this is going to work. So obviously the pi bond has moved towards B. B has effectively gained one electron because in this bond one electron already belonged to B. So one of the A's electrons has moved to B now, and A will lose, A becomes plus. So for A the situation is like this, and for B the situation is like this. So B is going to become minus, A is going to become plus, and the pi bond is going to go away. What about this situation? Now, for A, it is like this. Again, bond is moving away from A. And for C, it is like this. From somewhere, the electrons are coming to the bond. So A will become plus and C becomes negative. And remember, the total charge in all of these movements is the same. And let's take this case. Suppose I do it like this. What would this result in? For A, it will be resembling this. And for B, it will be resembling this. So A becomes plus, the bond becomes double, B becomes negative. So this is the final result of this. So now that we have seen the basic movement of electrons, now let's look at the most important part, the situations where resonance is exhibited. So I'm going to take various situations. There are basically 7 basic situations when resonance is shown. The first of which I'm going to talk about is called double bond conjugated with positive charge. So let me draw the structure. Can you notice this positive charge is alternate with this pi bond? And the alternateness has come because this bond is single. If two things are consecutive, then we say plus and double bond immediately. Then this is called cumulated. If they are together. If they are alternate, like they are in this case, plus is here, the pi bond is here, and they are separated by a single bond here. Of course, this bond need not be single always. That will do it at the end, but right now just take it as a single bond, as it is given as a single bond. So positive charge and pi bond are alternate. We call it conjugated. So cumulated and conjugated. That is the difference between the two. So now what happens? Now the positive charge is on one place, the pi bond is other. Where is electron deficient more? Positive charge. And where is electron density more? The pi bond. So the potential difference exists right here. So what will happen is the pi bond will move towards the positive charge. Electron will move from high electron region to low electron region, just like a current flowing. So pi bond will go from here to here and the positive charge will travel the other way around. So basically the movement is like this. Now there was a possibility that the movement could have been like this also. Now what would this effectively give me is a situation like this. And then the rest of the molecule. Now, in resonance, the basic idea is that one should not try to increase charges on atoms if you can help it. If you can't help it, it's a different case. But if you can help it, then try not to create more charges than what are already present. So rather than making this movement, and remember a bond can move to the next bond. So this bond is moved here. That way, I have only one atom having positive charge. Look at this carbon now. This has become positively charged. And again, this pi bond is conjugated with this positive charge. Again, this similar type of resonance will happen. And we get this. Structure 1, structure 2, structure 3. Now, what do these structures mean? What are these structures? Which is the actual molecule? None of them. It's the hybrid. It's the hybrid of these three. These three somehow have a cross. They may contribute equally, they may contribute differently. That is something that we're going to have a look at now. But the effective structure, the actual structure is the hybrid of these three. So now how do we calculate the stability? How do we figure out which is more stable and which is less stable? Because more stable the structure, more contributing it is going to be. So the order of stability of resonating structures which have total charge plus 1. If you look at 1, 2, 3, everywhere the net charge is plus 1 and they will always be same. Then the order of looking at it is like this. First of all such resonating structures, the one in which octet of all atom is complete is most stable and therefore most contributing. So if there is one structure where octet of all the atom is complete, and in this case of course octet of only carbon has to be complete because hydrogen cannot complete the octet. So if other than hydrogen for all atoms the octet is complete, then that is going to be most stable and therefore most contributing. Is there a structure like that? No. Because in this structure carbon is octet incomplete, this guy is incomplete, this fellow is incomplete. So you find one carbon atom in each which is incomplete and the rest all of them are complete. So the first point is not able to give us which is more contributing. The second is, next is that resonating structure in which positive charge is on the most electropositive element and then in that order. So if it so happens that positive charge in one case is on carbon, in the other case is on N, in the third case it is on O and the octet for all of them is incomplete, then that structure is supposed to be most contributing, most stable, in which positive resides on the least electronegative or the most electropositive element. So C plus structure is going to be more stable than N plus is going to be more stable than O plus. But in this particular case, even this doesn't work because in all the structures it is carbon which is plus. Alright, let's try and figure out a third point. The next thing, and remember you have to use these points in this order. So the next thing is resonating structures which are similar have equal stability. And look at 1 and 3. They are similar. Try to understand the meaning of the word similar and don't confuse it with the word same. They're not same structures. Same means it is one only. But in the case of 1 and 3, they're different. Look at 1. It is this atom which has positive charge. Look at 3. it has this atom which is positive charge. In drawing resonating structures, make sure position of atoms don't change, only the position of charge changes. So this atom is positive, whereas here this atom has octet complete. This atom has octet complete here, whereas this atom has positive charge here. So structures 1 and 3 are distinct, different structures, but they are similar. Different in the sense that different atoms have positive charge, different atoms have octet complete, but similar in the sense their energy would be the same. And therefore, if their energy is going to be same, they will have equal stability. So at least one thing that we can gather from point 3 is that structure 1 will be as stable as structure 3. And the fourth point, among resonating structures in which charge is on similar atoms, but the structure are different, the stability is decided by inductive effects. Now this is very, very crucial to understand. Most people don't get this point, or probably don't even know about this point. If I have two structures in which the positive charge is on similar atom, both is on carbon, but the structures are not similar, then the only way to figure out which is more contributing, more stable is by using inductive effect. Now one might ask why. The reason is, some people believe that this structure should be most contributing, most stable, because it can show resonance from either side. Remember, stability of a resonating structure cannot be explained by using resonance, because then it will never end. You say 2 can show resonance on either side. So by showing it on one side, it will go to 1. By showing it on the other side, it will go to 3. But 1, 2, 3 are already resonating structures of each other. 2 and 3 are resonating structures of 1. 1 and 3 are resonating structures of 2. 3 has resonating structures 1 and 2. So each has 2 resonating structures. So the stability of a resonating structure cannot be explained by resonance. You can only use particle effects, because the very act of drawing, remember we said we will draw particle structures and then take the hybrid of these. Those particle structures are taking the electron like a particle, and the particle effect is inductive effect. So when you want to calculate the energy of these individual particle structures, you cannot use resonance in resonating structures. The very act of using resonance is to explain the final ion or the final molecule. Now for each resonating structure, you cannot use resonance because those are not real at all. They are hypothetical canonical forms. Therefore, their stability can only be understood by assuming that we have to look for inductive effect, because those are particle structures. We need to calculate their energy. Since they don't exist, we cannot calculate their energy, but we can estimate their energy. We can say which is higher and which is lower. We cannot say how much, but we can say which is higher and which is lower. And therefore, it becomes very, very important at this time to understand that whenever you want to look for the stability of resonating structures, if everything else fails, the final thing is look and use inductive effect, because they are particle structures. We have treated the electron like a particle, and therefore that can only be explained by inductive effect. So how do we use inductive effect in this case? Well, what is it that you want stability to do? The only way a particular ion, we already know 1 is equal to 3, remember. We just want to figure out, is 2 greater than these 2 or is 2 less than these 2 in terms of stability. So obviously, the one in which the positive charge decreases more is going to be more stable, because more the decrease of positive charge, more it is going towards neutrality, more stable it will be. That is the ideal thing. Now, here what you need to understand is that if you look at 2, this is sp2 carbon, all are sp2 carbons here. Now let's call this carbon the one which is on the one which is directly attached to C+. Let this be called alpha, and this is going to be the beta carbon. This is the alpha carbon, this is the beta carbon. Whereas if you look at 1, you have an alpha carbon, you have a beta carbon, you have a gamma carbon, you have a delta carbon. Now tell me which has, now alpha beta and alpha beta are same. But here you got one more alpha beta and here you have gamma delta. Which one do you think has greater inductive effect? Alpha beta carbon or gamma delta carbon? Obviously, alpha beta carbon. These will have more inductive effect on this carbon than these two on this carbon. And what is the inductive effect of sp2 carbon? If you have seen the video, you will be able to answer this. It is minus I. sp2 is minus I. So what is happening is this alpha beta carbon are pulling the electron greater towards themselves than these gamma delta carbons. And therefore, what happens is, let me rub this off and make it a little better to read, otherwise it will create an issue. So what we're basically saying is that one alpha beta is common, so let's not write that. This alpha beta here is gamma delta here. So alpha beta carbon have greater minus I effect, they will pull the electron greater. By pulling the electron greater, the positive charge increases more. Now, there is one particular mistake that people make. They assume inductive effect, they look at inductive effect like a vector. They'll say, okay, somebody is pulling from here and somebody is pulling from here, so they cancel each other out. How can they cancel each other out? When two forces occur on opposite direction, we say net force is 0. But remember, the scalar value of those forces are acting on the object. Suppose you want to rip something apart. How do you do it? You pull from this side. You pull from this side. You want to open up something and you pull them apart. Now, if the forces were to balance, if the pull from here and the pull from here is same, then why is it getting ripped apart anyway? Because the scalar value of the forces is getting added. The vector part is 0, which basically means that the object is not going to move with respect to the ground if forces are equal. But the forces are acting on that object. The scalar value are acting on the object. Just imagine if somebody were to pull your hand from here and pull the other hand from here, what will happen to you? Now you can say it's going to be stable because the pulling is greater, is equal on either side. Your hand will get ripped apart. So the idea is that inductive effect, don't use it like a vector. If something is pulling from here and something is pulling from here, then both the pullings are getting added on this. So if there is a C plus in the middle and there is sp2, 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 this is pulling, the positive charge is going to increase because of minus I effect. And therefore, the positive charge on molecule number 2 is increasing compared to 1 and 3. And since 1 and 3 were already equal, the order of stability is like this. This is the order of stability. And if you haven't followed this, go through this video again, this part again. Now, the second condition for resonance to happen, the curtain opens, and that is to show you that when double bond is conjugated with another double bond. So if we have a molecule like this, can you see? Double, 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 all are conjugated. So we are going to figure out how to draw the resonating structure in this particular case. Now in this particular case, we can draw the resonating structure like this. What we do, we start from any one end. You can start from either this end or you can start from this end, doesn't matter, since it is symmetrical. You make the double bond go away from the other double bonds. So make this go like this. Now this will result in charge separation. Now you might wonder that I told you in the beginning that charge separation should not exist, but please understand, I said charge separation should not exist as long as you can help it. Here you can't help it, so you'll have to create charges. So once the charge separation happens, now it is a very simple thing. It's a double bond conjugated with positive charge, just like the previous one, and the resonance happens. The pi bond goes here, the plus moves to the next carbon, pi bond goes here, the positive charge again goes to the alternate carbon, and you got structure 1, structure 2, structure 3, structure 4. And structure, now we have got to look at the stability. Remember, the net charge is 0 in each of these structures. So the stability order of resonating structures having net charge 0 is calculated like this. Of all such resonating structures, the one in which no atom has any charge is most stable. So most stable is that in which no atom bears any charge. So obviously it is structure 1. Then the next is that resonating structure in which charge separation is the least, and then in that order. Remember, positive and negative attract. So they like to be as close as possible. In fact, preference would be positive and negative coincide and become neutral. So if you try to pull them apart, it's going to be very difficult. So you're going to increase the energy of the system as the distance between plus and minus increases. The potential energy of two opposite charges increases when you increase the distance. And therefore, the greater the distance, more is the energy, less is the contribution. So I think this would help us get the order 1 greater than 2 greater than 3 greater than 4. Now let's look at some evidence of resonance. Why do we talk about resonance? I mean, what happened that made us use this effect? Because of the following points. In this particular case at least, we can mention that all bonds were found to be in between single and double. Now, if structure 1 were to explain everything, then 3 bonds would be double and 2 would be single. Single, double. But none of the bond has been found to be purely single. None of the bond has been found to be purely double, which can only be explained if you can take the hybrid of 1, 2, 3, 4. Because if you look at 1, 2, 3, 4, all the double bonds are becoming single at least once, and all the single bonds are becoming double bonds in certain situations. None of the bond always remains single, none of the bond always remains double. Therefore, every bond has some kind of a double and a single bond character together. So, all bonds are between single and double bonds. And that is, of course, one of the main reasons why we talk about the hybrid and rather than just one of these structures. And on treating the molecule with bromine in CCl4, we get 4 products, 5, 6, 3, 6, 3, 4 and 1, 6. Now let's understand this part. Now, if double bonds were localized as it is in 1, what would happen is, if you add bromine to this, bromine adds to a double bond by becoming one bromine becomes plus, the other bromine becomes minus. This we will study when we do hydrocarbons. Now, and what happens is one pi bond moves to one of the carbon atoms, and this takes one of the bromine plus, the other carbon becomes plus, which gets the bromine minus, and effectively they add to an alkene. So where all should you get bromine? You should get bromine in these two, and you should get bromine in these two. This part is same as this part. So I should get a 1,2 product. I mean, if I can call this as a 1,2 product. I mean, either I get bromine attached like this, or I get bromine attached like this and not here. But what I get is, I get bromine attached here, I get bromine attached here as expected. I also get bromine attached here and here. I also get bromine attached one here and the other here. So I get a variety of products. One is called 5,6, other is called 3,6, then you have a 3,4, then you have a 1,6. Now let's look at the products first. The products would be like this. One attached to the 2 carbons at the end. This is called 5,6-dibromo-1,3-hexadiene. And if you don't know why it is named like this, go ahead and look at the videos that I made for IUPAC nomenclature. You must always follow a particular trend. In the case of organic chemistry, you must do the first lesson first, then the second, then the third, because organic chemistry lessons are interconnected. So they have to be done in a particular order. So go through all the nomenclatures first and then start with general organic chemistry. And that to follow all the videos one after the other. The next molecule is this one. One bromine attached to the terminal one attached to somewhere in the middle. And this is called 3,6-dibromo-1,4-hexadiene. And then there is one like this. This is 3,4-dibromo-1,5-hexadiene. And there is one molecule like this, which is 1,6-dibromo-2,4-hexadiene. Now, why is it like that? Why is it behaving like that? Now, I get this product because the double bond is here. I get this product because the double bond is here. But why do we get products here and here? That's because one is minus, the other is plus. So structure 3 is able to explain this product. Why do we get one bromine here and one bromine here? Because this is minus and this is plus. And as I said, Br plus and Br minus are formed and they attack the molecule. So I'm able to explain all the products only by using the contribution of 1, 2, 3 and 4. Now I'm going to ask you a question which I want you to do on your own and then look back into this video to see the solution. I want you to tell me which of these products is going to be greater in value, greater in quantity, which is going to be major, which is going to be less, and what is the order of these 4 products. So take a while, pause the video, think about it and write down and then look into the solution in this particular video. Now, first of all, if you remember, structure 1, which was the neutral structure, which had the double bond here, that is able to give you this product. Moreover, this product is also formed due to structure 1 because it has a double bond here. So structure 1 is able to give me these 2 products. Whereas it is structure 3 which gives me this product. It is structure 4 which gives me this product. And the stability order was 1 greater than 2 greater than 3 greater than 4. Now 1 and 2 will account for this. 1, this is due to 1 and 2. This is due to 1. This is due to 3. This is due to 4. So since 1 and 2 contribute more than 3 and 4, we expect these 2 products to be greater in amount, and since these 2 are formed from 3 and 4 respectively, therefore we expect their content to be less and 4 should be the least. But life is not that easy. The product yield is 1,6, which we expect is the least, is the most in value, then 5,6. These 2 are 5,6 is okay to understand because it is formed by 1 and 2, but 1,6, how the hell is this highest? This was formed from structure 4. And then 3,6, which was the second least contributing, and then 3,4 is the least even though it is formed by structure 1 which is most contributing. Why the hell is this happening? The reason is like this. Please understand, the structures 1, 2, 3, 4 don't exist. They are structures that we have drawn to make ourselves happy so that we can understand the hybrid. The structures 1, 2, 3, 4 don't exist. But then you might say, but they contribute, don't they? Yes, they contribute. They contribute to the actual hybrid. But then why the hell did that product form most, which was having the contribution of the least resonating structure? Well, the thing goes like this. Look at 1,6. You will notice that the double bonds are conjugated amongst themselves in the product itself. So here the product shows resonance. This is the key here. Look at 3,4 and 3,6. You don't see any resonance. Double bonds are not conjugated. Double bonds are not conjugated. But look at 5,6. Double bonds are conjugated. So 1,6 and 5,6 dominate because both of the products show resonance, whereas these 2 don't show resonance. And since the resonance is generally going to increase stability, that is the very reason why resonance occurs, and therefore 1,6 and 5,6 products are more stable than 3,6 and 3,4. Therefore they are formed more in number. Now comes the question, why is 1,6 greater than 5,6? That's because of this reason, that here one of the double bonds of 5,6 is terminal. And when we do alkanes, you will realize something, and perhaps you will realize it much sooner also in this lesson itself, but later on in this lesson, in some other video. Terminal double bonds are less stable than non-terminal double bonds. For the time being, you take it like this. For the time being, you accept it. Later on, when I explain a phenomena called hyperconjugation, you'll understand why it is so. So in the case of 1,6, both double bonds are non-terminal, whereas in the case of 5,6, one of them is terminal, so 1,6 is greater than 5,6. Now what about 3,6 and 3,4? In 3,6, at least one double bond is non-terminal. In 3,4, both are terminal. So it is less stable. So 1,6 product is most stable because the double bonds are conjugated and non-terminal. 5,6 is next since double bonds are conjugated, but one of them is terminal. 3,6 is next as one of the double bonds is non-terminal, while 3,4 is the least as both are terminal. Now comes the question. The resonating structures predicted something else. The product stability predicted something else. Which one do we follow? Well, in general, now don't kill me for this, but in general, product stability overrules everything. But there may be instances, because remember, organic chemistry is life. The difference between physics, chemistry and mathematics, if I hope the instructors of physics and mathematics are not going to kill me for this. Physics, chemistry, mathematics, the basic difference is that physics deals with non-real situations. I mean, when you study physics, don't you see a ball rolling on an inclined plane, smooth, frictionless plane? Can you ever have a plane like that? Or even if you do use coefficient of friction, don't you assume it to be constant? But can you have a surface with constant coefficient of friction? And even if the coefficient of friction changes, it will change by a single equation. Is it possible like that to ever have a surface like that? So physics deals with hypothetical situations, ideal situations. Just like you must have studied ideal gas. Pretty simple. Mathematics is arbitrary. Numbers that we have invented on our own. Chemistry deals with reality. So in reality, things are very, very complex. So if you were to ask me, will product stability always overrule? It might. But there may be cases where resonating structure may actually overrule the product stability if the difference between the product stability is not that great. So if you want me to commit to something, I cannot. Though I don't know of a case where resonating structure wins over product stability, but I'm sure there might be. And even if they are not, that is mere coincidence. Exceptions are basically a rule in chemistry. So now I go to the third situation. Double bond is conjugated with a negative charge. So here is a negative charge on oxygen, and as you can notice, it is conjugated with the double bond. So negative charge is here, double bond is here, they are conjugated, and negative charge being more electron dense will move towards the pi bond, and the arrow shifts like this, and this pi bond will shift to the carbon. So the next structure looks like this. Then again minus will come here and this pi bond will go here. You get the third structure like this. So you got 1, 2, 3. And what is the stability order when the net charge is -1? Of all such resonating structures, then one in which negative charge is on the most electronegative atom is most stable, and then in that order. So 1 is most stable. Negative charge should be on the most electronegative atom. But here the negative charge in 2 and 3 are both on carbon. So 1 cannot decide the fate of 2 and 3. Resonating structures which are similar have equal stability. This also doesn't help us with 2 and 3 because 2 and 3 are not similar. They are different. So the third point will help us. Again, inductive effect. If the charge is on similar atoms but the structures are not similar, then use inductive effect. So how would you use inductive effect? Pause the video and look for the stability of 2 and 3 yourself. Now remember, here there is a negative charge. Alpha carbon, beta carbon, alpha carbon, beta oxygen. Now look at structure 3. Alpha carbon, beta carbon, gamma carbon, delta oxygen. And remember, they are all -I. They are all withdrawing electrons. And what will happen when they withdraw electrons? Negative will decrease. Where will the negative decrease more? Obviously in 2. Because there is 1 alpha and 1 beta. Here it is 1 alpha and 1 beta again. And that too beta is oxygen. Much more closer to negative charge. Its pulling will be greater. More pulling on the negative charge, lesser the negative charge would be, more stable the structure would be. So the order is 1, 2, 3. The next one, let's move quickly. The next one is a double bond conjugated with a lone pair. Well, lone pair can be treated just like a negative charge, just behaves like a negative charge. The lone pair comes here and the pi bond shifts to carbon and you get this one. then the negative 2 goes here and the pi bond goes to this carbon and you get this one. 1, 2, 3. And how do we look at neutral structures? Structures with net charge 0, we already seen in double bond resonance. Of all such resonating structures, the one in which no atom has any charge is most stable, which is 1, and then the opposite charges should be as close as possible, which means 2 will be greater than 3. So again, the order is going to be 1, 2, 3. Now I'm going a little faster here because I don't want to take too much of time. I'm already past 56 minutes now into the recording, so I want to make it faster. So if you find it faster, pause the video, replay it, listen to what I'm saying, and then rewrite it. That's the advantage of a video. You can pause and play again. Alright, now we go to the 5th point. There were 7 of them. We're on to 5th. Double bond conjugated with unpaired electron. Look at this one. There's an unpaired electron and there's a double bond here. They are conjugated. Now it's a single electron movement, so I'm going to show half an arrow. So one electron moves here, one electron moves here, and this carbon becomes a radical. It's called a radical. Again, the similar thing happens. One electron moves here, one electron moves here, and again oxygen becomes a radical. 1, 2, 3. Stability order of structures having no charge and having one unpaired electron. You can treat the unpaired electron just like a positive charge and look into the stability. If this, instead of this dot, had it been a positive charge, what do you think would have been the stability? Just write down the stability and then replay the video again. Now, of all resonating structures, the one in which the unpaired electron is on the least electronegative is most stable. So obviously 3 is least stable because it is the most electronegative atom. And the same would have resulted had it been a positive charge. A resonating structure which are similar have equal stability, well, none of them are similar here. And then use inductive effect, the last part. And so just take the unpaired electron like a positive charge and look into the inductive effect, and you will yourself figure out that 1 is greater than 2 and 2 is greater than 3. And the next part is the lone pair conjugation with a positive charge. And this is the molecule. Right now the positive charge is conjugated only with a double bond, but then very soon it's going to be conjugated with a lone pair because this plus is going to move here. And you are going to get this, and the lone pair comes here, and you're going to get this 1, 2, 3. And remember, the net charge is +1. So what was the order? I'm just repeating these points because we've already done them once. When the net charge is +1, the order of resonating structure was first look for octet complete. And if you look at structure 3, all atoms have their octet complete, including nitrogen. Whereas structure 1 and 2 have one carbon always incomplete octet. The structure 3 is most contributing, most stable. Now you might wonder, how the hell is this more stable when N, the most electronegative element, has positive charge? Remember, the first order of rule is not where the positive charge is located, it's whether all the atoms have the octet complete or not. That is the most crucial point. So next is that resonating structure in which the positive charge is on the most electropositive element, and then in that order. Remember, I always told you, go in this order. And the third is a resonating structure with equal stability, the ones which are similar have equal stability. And 4 is among resonating structures in which charge is on similar atoms but the structures are different, we look at inductive effect. So we are going to look at inductive effect to be able to determine the stability between 1 and 2 because they are not similar. And obviously 2 will be least stable because here N is highly electronegative, it's going to pull, it's right next to C, whereas here the N is very far away. It is the third atom from C+. So 2 will be least stable, so it's 3, 1, 2, 3 octet complete, 2 because of inductive effect. And then we come to point number 7, the last point, but of course we have certain stuff to do even after that. This is the lone pair conjugation with an unpaired electron. You can see an unpaired electron here and you see a lone pair here. Now I want you to pause the video now. I want you to write down the resonating structure and then play the video. Well, the resonating structure can be drawn like this. One electron is transferred to carbon and you get this. Now many people are going to do this. They will draw NH2 and CH2 like this. They will put one electron here, they'll put one electron here. It's not possible because N will have then more than 8 electrons, because it's already got one bond. Sorry, let me rub this. It's already got one bond, which is 2 electrons. 2 plus 2, 4. Flow 4 plus 2 hydrogen electrons, 2 hydrogen atoms, 4 more 8. But when you put this, it becomes 9. It cannot take 9 electrons. So it cannot happen like this. Or some people will go to the extent of writing, NH2 like this. And they'll say, okay, how about this one? Again, this is not going to work because now the carbon will end up having 9 electrons. So the only way possible is for nitrogen to transfer 1 to carbon. Radical nature goes from carbon to N, and lone pair goes from nitrogen to carbon. And the stability order is very simple. You know that structure 1 is not having any charge, and therefore and the unpaired should be on the least electronegative atom. So structure 1 is going to be more contributing, and the ones which have similar have equal stability. Then you use inductive effect. Same logic everywhere, not different at all, and therefore 1 is greater than 2. Now we also need to understand something. There are certain other cases also of resonance. The first of which is that the conjugation need not be necessarily via a single bond. It could be via a double bond. That means the bond that is in between need not be single. This bond need not be single. It could be double also. But resonance will only happen between these two double bonds. This is not going to be involved in resonance, but it can separate the two double bonds. So the ones which is separating need not be always a single bond. And next point is that wherever we have seen a double bond, you could even have a triple bond. But remember, if you have a triple bond, then only one pi bond will be involved in resonance, not both, because the orientation of the orbitals will be such. So wherever we have studied that a double bond is conjugated with something, the double bond could also be a triple bond. Okay, now let's get the things going fast now. In general, resonance effect is associated with p orbitals, which may be empty, completely filled, or partially filled. But there are instances of d orbitals also delocalizing electrons. This is referred to as d orbital resonance. It is a common misconception that resonance structures are actually transient states of the molecule, with the molecule oscillating between them or existing as an equilibrium between them. That is because we use the wrong word called resonance. Every time we always you have a misnomer. Something called resonance basically could sort of indicate that it is going from here to here, resonating. It's moving, like a pendulum. No, it's not moving from here to here or here to here. There's no equilibrium there. These structures in fact don't exist. The molecule exists in only one form, which is the hybrid state. However, these individual contributors cannot be observed in the actual resonant stabilized molecule. Any molecular ion exists only in one form, the resonance hybrid. And due to confusion with the physical meaning of the word resonance, as no compound actually appears to be resonating, it has been suggested that the term resonance be abandoned in favor of delocalization. Now, as I said at the beginning, resonance effect and mesomeric effect can generally be used as synonyms, but there is a slight difference according to IUPAC Gold Book. The difference is that resonance effect represents all the contributing canonical structures of a molecule in which all electrons are localized, while mesomeric effect represents the more delocalized hybrid state. So one can conclude the resonance effect gives rise to a mesomeric state. So the hybrid is mesomeric state and the contributing structures are resonating structures. So resonating structures give a mesomeric state, the hybrid. Since resonance effect is a relative effect, an atom or group may show both releasing or withdrawing nature of electrons by resonance. It depends on the atom or group of atoms it is attached to. I'll show you that. However, some groups will exclusively show releasing or withdrawing nature of electrons by resonance. And the ones which show plus M, that is withdraw electrons, release electrons, are these. These are the ones which release electrons by resonance always. They will never withdraw because they have nothing to withdraw with. They all have lone pairs. One thing common in all of them will be lone pair. Anything having a lone pair has a tendency to give electrons by resonance. And the ones which exclusively withdraw by resonance are these. They always withdraw. They cannot release because they don't have a lone pair. So they don't have any lone pair to give. And groups that can show both plus m and minus m, depending on the groups attached to, are the phenyl group, the vinyl group, and the chlorine atom. Chlorine atom because it has d orbitals along with lone pair. So with lone pair it can give, and with d orbitals it can withdraw. Though we generally call resonance as involving p, but d orbitals also get involved and they're called d orbital resonance. So to make it more clearer, I'm not including this in the case of plus m effect only. And it is unwise to categorize groups in the increasing or decreasing order of resonance effect. As being a relative effect, the extent of resonance depends on the group it is attached with. This we've already talked about in the beginning. It is unfair to talk about groups saying this has a minus m greater than this, or this has a plus m greater than this, because it varies depending on the group it is attached with. It's a relative effect. Now, drawing the resonance hybrid, in some cases you can draw the resonating hybrid, though the drawing would not be exactly the actual structure, but we can get some sense of it. So this structure gives rise to this structure, and this is the hybrid. So these are the two canonical forms, and this is the hybrid. We can say, okay, electrons are partially here, they are not completely here, so we can show them by dotted. But remember, this is not the actual structure. The actual structure is not dotted. Electrons are delocalized everywhere, and that delocalization is being shown by these dotted lines. And let's quickly swift through this lesson now. Resonance energy. Resonance energy is defined as the energy difference between the mesomeric state that is most stable, the actual one, and the most stable resonating structure. So if you look at energy wise, these are the two forms of benzene, and this is the hybrid. And the difference between the state of the hybrid and these two, since these two have equal energies, it is easier in this case. If there are unequal energies, then we compare it with the most stable one, and this gap is called resonance energy. And in the case of benzene, it is 36 kcal. So quickly, now let's end this lesson by looking into the difference between the inductive and the resonance effect. And I have a small spelling error here. Please don't mind that. So inductive and resonance. So now I correct the spelling. And the differences are like this. Inductive, as we said, is a manifestation of the particle nature of the electron. Resonance is the manifestation of the wave nature of electron. Inductive is the movement of sigma bonded electrons. Resonance is the movement of pi bonded electrons. And inductive, remember, is an always effect. It's a need-based effect. If you want it, it will give. If you don't want it, it won't give. But inductive doesn't care. It will give always, take always. It is a relative effect with respect to hydrogen atom as standard. It is a relative effect with respect to the group with which it is attached to. And the strength of the inductive effect of a group is constant and does not depend on the group it is connected to. And as I said now, the strength of resonance effect of a group is a variable and it depends on the group it is connected to. So if the group really wants electrons and this can give, it will give. If it doesn't want that much, it won't give that much, the resonance effect decreases. And inductive travels only for a short distance. After 4 atoms, 3 or 4, or perhaps 4 and 5, it vanishes. Resonance travels as long as conjugation is present. And finally, it's a real effect, inductive. Resonance is actually an imaginary effect which is given to explain the properties of a molecule, which ideally should be dealt using molecular orbital theory. And it's a weak effect, inductive, and this is generally stronger than inductive, but not always so. As you have in chemistry, there are always exceptions. So that is the end of resonance effect. I know there are certain parts I did a little fast because I didn't want the video to go beyond 1 hour and 15 minutes, which is still going to go. And therefore I wanted to sort of do it a little faster, but you can always pause the video, look into what I'm saying, check it out. And at the end of this video, if you still have certain things which are not clear, if it is possible, go back and see the video again. If not, you can, if you have any questions, any comments, any suggestions, any queries, any doubts, anything that you would like to talk to me about, you can drop them in the comment section below. I'm putting the link of the video 1, the part 1 of the video series in the description. And one thing that I wanted to mention before I end this video is the fact that my videos are going to be pretty long. Now, the ideal time for a YouTube video is generally supposed to be 15 minutes. But in my case, since we're talking about academic lessons, we're not talking about a product review. I have another channel in which I review products and in which, I make very short videos, at least much shorter than these videos. But in the case of lesson videos, it's not possible to shorten them. We have to, in fact, I have rushed through this video, which I really would not like to, because I think even my camera battery is going to die very soon. So the fact of the matter is that I'm trying my best to make the videos as short, but I cannot do that at the cost of not being able to explain it well. And therefore, what I would first of all recommend to you is don't get bogged down by the fact that when you look at the size of the video, you say, oh my God, it's 1 hour plus, I'm not going to watch it. Then you should not study. If you want to study, if you want to understand something, you have got to spend that time, number one. Number two, the second point is that before watching these videos, make sure that you have that much amount of time to watch. In fact, double the time. Because you're going to have to watch, you'll pause, you'll write certain things, you will try to find out something which I've asked you in the video and then play it back and then check for yourself whether you answered it correctly or not. So all of those things being done, so you need double the time. And if you don't have that much time, don't watch these videos. It won't work for you. Don't watch it like I've got 20 minutes now, I'll watch it for 20 minutes, I'll pause and I'll come back. It's not like a movie or watching in Netflix or Amazon Prime. It is something which is academic related. It has to be done in one shot. Now, I could have made these into 7 parts where I showed each of those cases. I could have made them into smaller pieces. It doesn't work. Resonance effect has to go in one go. Inductive went in one go. Now, there may be videos of irregular size. For example, the next one that I'm going to do again is going to be a very long video. But the one next to that called hyperconjugation is going to be a very small video. So different sizes are going to be there depending on different sections. I've already broken them into 13. I cannot break down them further. So I would want you to have sufficient time and only then watch the video, because only then this video is going to work for you. And I hope it did work for you. So if you haven't subscribed to my channel, I encourage you to subscribe to this channel. Consider subscribing. I post a lot of chemistry videos. You can have a look into my playlist, into all the videos that I've posted, and check for yourself whether they are useful to you or not. And if you find them to be, please do hit the subscribe button. You'll get a separate panel in your YouTube channel where you can actually reach my channel, and you will get a notification every time I post a video on my channel. And if you like the video, please do hit the thumbs up button. This is Kalyan Kumar signing off. Have a great day. Goodbye and thank you for watching.